So after coffee, we have Aparna Bhattacharya talking about road planets or white orbit planets around white dwarfs.
All right. Hi, I'm Aparna. I also work with Dave Bennett and Sean Terry in the University of Maryland. So I would actually go to the very unpopular opinion about like bound planets. We are going to start from there. So we like the last two talks we saw about doing, observing with Keck AO and doing mass measurement, but how do we actually do it? So there are two equations. There are two equations two mass distance equations we get from the geometry of the microlensing. So in both equations, you see the mass has a relation to the distance, and they are connected by either the angular Einstein radius or they're connected by microlensing parallax. So if we happen to get both of these parameters from the light curve analyses, then we can solve these two mass distance relation and we can get the mass as a function of parallax and Einstein angular radius. Okay, but most of the cases, we don't get both of these. We either get one of them or we get the parallax, but we don't get the direction of the parallax. So as a result, we usually get maybe one of these equations. And then what we have to do is we have to wait a few years and we have to get high resolution observation with Keck AO or HST. And with that, when we can detect the lens, then we can get from mass luminosity relation, we can get a relation between mass distance. So that will be our second mass distance relation. We use that mass distance and one of these to get the mass. So that's what we are doing to get the mass. So that's for bound objects. So this is actually just a cartoon diagram of what Sean already showed you. Basically, we don't get to see the source is so bright and magnified during the peak of the microlensing event that we actually can't see the lens. And in a few years, as it's separating out, we can finally start to be able to detect the lens in the high resolution image. So this is an example of what it actually looks when it's observed in Keck, HST, and 3 different passbands, and you can see the source and lens. This is about 33 milliarc second separation. This was taken near simultaneous with both HST and Keck. And what it does is when we took that high resolution observation and we detected the lens, what it did is that we also detected the direction at which the lens is moving. So we can constrain the direction of motion. So from that direction of motion, so this was actually the parallax that was measured from the light curve. But once we measure the direction, this is the difference that happens. So this goes from here to here. That is how much the constraint comes because of the direction of motion that we have been able to calculate. So this pink curve over here is actually what we get from the light curve, and this green curve over here, which is also the mass distance relation, is what we get from the measurement. So it reduces from this pink curve to green curve. That's how much improvement we get. And so these lines over here is from the luminosity, we get the mass distance relation. So the blue is for the blue passband and orange is for the red passband. So when it actually crosses here, that's where we are getting the mass. That's where we are getting the mass of the lens, pulsar, and the mass and the distance of the system. So now, I would come back to a recent paper that Sean Terry led. This is actually the event where the lens is actually 50 times fainter than the source. And the lens is 110 milliarc second away. So it's also one of the source subtracted image. And you can see that this is really faint. And when we actually reduce, when we do dual star fit, then we get actually better subtraction, which shows that this was the lens. But this is the faintest we have got with respect to the source. And even in this case, it was 110 milliarc second away. And so if this was still a main sequence lens event. So if we try to get something even fainter than this, so if it's a white dwarf lens, this will be very hard to detect with Keck. And with that, I would come to the point that, so until 2021, there were 4 planetary systems that was detected around white dwarf event, white dwarf star. And all of this, you can see the different techniques. It was not microlensing. And the distance is 23 AU, 2500 AU, 1500 AU, and 0.07 AU. So what is missing from this list is something, a planet that is only a few AU away from the host star until 2021. Then the first macrolensing planet that was discovered around white dwarf was MOA 2010 Bulge 477. This was actually published in 2021. So in this case, you can see this was an event observed in 2015 and 2018. And initially we thought this would be the lens star, but this star did not really move much. And so here it shows actually where we expect the lens star to be. And we don't actually detect any lens star, but if it was a main sequence star, we would have detected it. So based on that, so this is actually a graph that shows the H-band magnitude and the distance. So here's the Keck detection limit and all these masses here that shows that if it was a main sequence star, this is where we would have observed the magnitude. And since we don't observe anything from that, we actually get to the point where this is going to be very likely a white dwarf at a 2 kiloparsec distance with a planet of Jupiter and at a separation of about 2.8 AU. So the thing I would like to point out is that our Jupiter in our solar system is 5.2 AU from the sun. So that means this is like the closest, the first planet around white dwarf that we got that is only few AU away. Now the second event was KMT 2020 Bulge 0414. Here also we see the minimum main sequence lens brightness we expect like this. But again, from Keck observation, it is found by Chang et al. That we don't see any lens from which we actually conclude that this is going to be a planet, which is about 1.7 by Earth mass, around 2.17 AU. So the whole point is that we are finding more and more planets around white dwarf in few AU distances now. And with Roman data, we will see more and more of these. So I don't want to go in too much detail about this, but basically it's trying to say that we can have very different possible system evolutionary history. And the more and more data we get on these things about bound planets around white dwarf, the more and more we will know what it's going to be like. There's another data from Veras et al. 2016. So we find that as the initial mass of the star goes up, the mass loss rate goes up. And if there's higher mass loss rate, then that envelope, when the star ejects the envelope, it's more likely to push away the outer planets even further away. And that means that we can have planets that are at very high orbits. So when we think about free floating planets and confirming if they are free floating planets or not, we need to consider these kind of cases, especially cases like white dwarfs that are very hard to actually detect. There's still a few more events with no host detection, but I I don't want to comment too much about them because these analyses are still going on. But the whole point is that we used to think that bound planets around white dwarfs may be uncommon, and that may not be true. Finally, like how can we detect and confirm these planets that could be FFP or wide orbit planets around white dwarf? And for that, we can say, we can take like Dave mentioned, we can take JWST simulated, JWST deeper observations. So this curve is a little complicated to understand. But the point here is I would like you to see the F ratio. So this was also a simulation done by Jay Anderson. And as you see, the flux ratio varies from 1/250 to 1/100. So what he did is like he injected, like with a source and a lens, he injected lens that is 250th times fainter than the source. And then in the next column, 200 times fainter than the source. And then it goes on to 100 times fainter than the source. And he injected at different offset, different separation of pixel. And he injected at several like radii. So it doesn't matter like what direction you inject. And then he tried to see if he can recover those. And these rate points are the ones that would show if you can recover them or not. And as you see, you go from this side to this side. So as the flux ratio gets higher, I mean, the flux ratio gets lower, you see that at about 1.4 pixel, you almost get like 100% chance of recovering them. So basically, if you have a star, a white dwarf that is 100 times fainter than the source star, and if it is at about 45 to like 60 milliarc second, you have 100% chance of recovering it. It's a much harder when it is like 1/250th, then it's much harder over here. Then you need the separation to be higher, like about 3 to 4 pixel offset. So with that, I would have my final slide is that the next talk is about Roman Galactic Exoplanet Survey, and it will discover hundreds of FFP, and we need to actually make sure to know how many of these are actual FFPs, because we already know it is very hard to detect wide orbit white dwarf than main sequence stars. One of the first things we can do when Roman data starts coming in, because Roman will have similar resolution as HST-IR, is that on FFP is to confirm the existing FFP candidates and compare them with MOA results. We can also compare the statistics of bound planets with no host detection or white dwarf host detection to estimate maybe the probability of actual FFP versus wide orbit bound planets. And then finally, we can take maybe deeper observations with JWST or future ELTs to confirm that they are not wide orbit planets around white dwarf. So that's all.
Thank you, Aparna. Is there any questions?
Great talk. Does it make any sense to reobserve these in the UV? The white dwarf should be much brighter than.
I think it would be maybe harder to observe them. I don't know. What do you think?
Pretty bad.
So I didn't hear.
Extinction is pretty bad in UV.
Oh, okay. So we wouldn't have much opportunity to see. Okay, thank you.
So it seems like things that are wide bound to white dwarfs could actually be a pretty good background for free floating planets, just because it's so hard to tell that the white dwarf is there. Do you have any idea, given what you've seen so far, sort of what the relative yields you would expect in Roman for these two different populations would be? Do you think it's going to be most, is it 50-50 or is it 90-10 or what?
I think that would be hard to predict with very small amount of data that we have now. I think.
Yeah, roughly 20% of all microlimits should be.
But free floating planet, like,
I mean, who knows what the demographics of planets are.
okay.
If they're equally well represented around white dwarfs and other stars, then 20% of the planet should be
Okay,
of order.
okay.
But also, what percent of FFP events are true wide order?
Cool.
One question back there.
Oh, yeah, very nice talk. So you mentioned that bound planets around white dwarfs were thought to be uncommon. But is that actually true? Because I thought there's a big fraction of white dwarfs that are polluted, the atmospheres are polluted, and we think that planets perturb some asteroids or comets or something material to cause that pollution. I thought there was a high fraction of white dwarfs that are polluted. So I thought the theory suggests that there's some plants around this white dwarf. So what is that true? I mean, do we actually think it was uncommon or?
I think so I really referred or read through the Veris 2016 paper, and it's very common to see pollution around white dwarf, but also sometimes they expect that the outer planets migrated. So that's why they saw there were a bunch of there were two discoveries that they saw planets really far away, and it's like planets like this can really be a cause for thinking, oh, this is a free floating planet in microlensing, and then we just find it's really far. It's a very wide orbit planet to a white dwarf. So that's what I kind of wanted to point out.
But yeah, I mean, what you talked about is that planet at 5 AU that might be very compelling for it to be perturbing material and or to pollute a white dwarf. So it's really that's where you need the planet to be.
Yeah.